I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we are going to see the topic optical windows and also the attenuation. So, the optical window is the optical portion of electromagnetic spectrum which passes through the atmosphere all the way to the ground. Most of the electromagnetic wavelengths are blocked by the atmosphere. So, this is like a window that lets through only a narrow selection of what is out of there through the sun is particularly active in the past wavelength. It is called optical because the wavelengths we can see are all in this optical communication range. The window runs from around 300 nanometers in ultraviolet B at the short end up to the range of the eye can use. Roughly it is 400 to 700 nanometer and continuous up through the usual visual infrared to around 1100 nanometer, which is in the near infrared range. So there are also infrared and radio windows that transmit some infrared and also the radio waves. So the radio window runs from about 1 centimeter to about 11 meter waves. And the features are, in medical physics, the optical window is the portion of the visible and infrared spectrum where living tissue absorbs relatively little light, and this window runs approximately from 650 to 1200 nanometer. At shorter wavelengths, light is strongly absorbed by hemoglobin in blood, while at longer wavelengths, water strongly absorbs infrared light. In optics, it means usually, at least mechanically, sometimes optically f height or f beat, depending on resolution requirements. So, a piece of transparent and optical material that allows light into an optical instrument. And now the attenuation and dispersion. Attenuation, we know it is a signal reduction. So, and it is given by the formula alpha is equal to 10 divided by L log of P in divided by P out. And this attenuation, that is signal reduction, is expressed in decibels per kilometer unit. And here L represents the fiber length which is used for fiber communication, and this attenuation is caused by either absorption or scattering and bending of optical fiber. And P in the formula refers to input power, P out refers to the output power. And if we see the absorption, the first case is intrinsic absorption, and it is by the glass material itself, and it is due to absorption bands in ultraviolet region, and tail of the curves enter the operation region, and the intrinsic absorption is small when compared to IR absorption. And here E and loss is inversely proportional to the wavelength, and it is typically 0.1 decibels per kilometer at 1200 nanometer wavelength. So, and this attenuation follows empirical relation as Urbach rules, that is E is the photon energy that is given by alpha ultraviolet is equal to C E power E divided by E naught. Here the C and E naught are empirical constants. And the next case is the scattering. Scattering is due to microscopical variations in material density. And we know that glass, optical fiber is made up of glass, and glass is a randomly connected network of molecules having higher or lower than average density. And it has the compositional fluctuations of silicon dioxide, germanium oxide, and phosphorus P2O5. And this gives refractive index fluctuations. If fluctuation distance is very small with respect to wavelength, cause Rayleigh type scattering of light, and that is in the Rayleigh type scattering, photons moving in all directions, and every signal strength gradually reduces and it is proportional to lambda power minus 4, so that we can say it scattering reduces when increase in wavelength. And another type of scattering called Mie scattering. Here the Ra fluctuation distance comparable to wavelength, and this Mie scattering can be reduced by various methods. One is we can reduce the imperfection due to manufacturing, and carefully controlled extrusion and coating will reduce the Mie scattering effects, and increasing the fiber guidance by increasing del value is also another format which is used for reducing the Mie scattering. Thank you.